So I would like to ask you first, what will be the highlight of your talk in simple
Yes.
words, so that it's an outreach stuff. So.
Yes. So I will talk about some results from my experiment, which is called LHCb. It's one of the experiments at the LHC that studies in particular the physics of the so-called beauty quark. And I will talk about a particular set of measurements which try to reach the maximum precision on some observables and compare them with the standard model predictions, which is the theory that describes all phenomena that we have seen very well, all the measurements that we have made so far. And looking for deviations.
So you look for verifying the standard model, but also deviations.
Yeah. Precision physics based on measurement of the beauty quark, and verification of the standard model with the hope to find some deviations, and we do find some deviations. So,
do you think they will stay?
This is hard to predict, but there are some quite solid measurements that do show some deviations. It could be maybe an effect of statistics, and with more data we will be able to say whether this is real or not.
Okay, thank you very much. Since you have been so many times here and you have seen the progress we are making, and we were brave enough also to make this conference in person, could you tell us a few words about what we are doing so many years?
Well,
we are about 40 years.
Okay, I haven't been here 40 years, but I've been here long enough.
The new thing is that we rebuilt all these buildings, so next year we hope we have office space there.
Okay. No, I think it's a great event. It's a great location. First of all, it's always beautiful to be here in Corfu and to be in Greece, and in such a lovely setting, and it's nice because it brings together established scientists from all over the world in a very informal and inspiring environment, together with students, and so one hopes that this exchange can attract these students to continue their science and their research work.
Very good. So this brings us to the last question.
Yeah.
What is your suggestion to the young people, to the young researchers that you see? There are plenty of them around.
Yes. Well, I think that working in science is a big privilege, and I think young people should really make an effort and try to build a science career if they have an interest and a passion for science. If they do, they should persist. Yeah. They shouldn't give up. It's not always easy, but especially women, I think we need more women in science, and I think having a scientific career is extremely rewarding, and research career is beautiful because you have a lot of freedom, and it can also be tough, but certainly
one has to work hard.
Yeah, one has to work hard, but it's extremely rewarding. So I encourage young people to follow this line. Okay, so it's really a pleasure to be here again in person after all this time. And so thanks to the organizers to have given me such an opportunity. And today I will cover the subject of rare decays and tests of lepton flavor universality
in B quark flavor physics at LACB. And actually, I had a short chat with Matthias Neubert there, and he was saying this is a workshop, this is not a school. But in fact, I read it is in institute, you said. It's school and institute. So mine will be a lecture for a school. Okay, so let me start by introducing the subject. Why is it interesting to study flavor? Well, we have a theory, which is the standard model, that describes at the current level of the experimental precisions and at the energies that we have reached so far, all the measurements, all the phenomena that we have studied, essentially. And it is the best tested theory of nature at a fundamental level. But still, there are many very basic questions that you know. What determines the observed pattern of masses and quarks and leptons? Why are they arranged in generations? And why 3? And in the standard model, the only interaction that distinguishes the 3 flavor is the interaction of the matter fields with the Higgs boson, the so-called Yukawa interaction. And the complex phases that are present in the Yukawa couplings are also the only source of CP violation. And we know that CP violation is required, is one of the conditions that is required to explain the matter-antimatter asymmetry in the universe. So, are there other sources of flavor and CP symmetry breaking besides the standard model Yukawa coupling? And to be able to answer these questions is likely to shed light on physics beyond the standard model. And flavor physics may actually provide the first such indications of physics at energy scales that are not directly accessible to direct searches. And as I said, the CP violation is connected to a very deep and fundamental question, which is the matter-antimatter asymmetry of the universe. So where did all antimatter go? And what led to the disappearance of antimatter, assuming an initial symmetric state? We know that there are antiprotons in cosmic rays, which are consistent with secondaries due to the interactions of cosmic ray protons in the interstellar medium. We know that we can produce antimatter in accelerators. We do that all the time. But apparently there is no antimatter around us. And this looks really, really strange. So where did it go? Why is the universe 100% matter asymmetric? And can the standard model explain the barium asymmetry of the universe? The answer is no, because the CP violation in the standard model is too small to explain it by several orders of magnitude. So CP violation beyond the standard model must exist. Where might we find it? In the quark sector, as deviations from the CKM predictions. And this is the subject of the next lecture by Neville. And or in the lepton sector as CP violation in neutrino oscillations, or as in other new physics, because almost all TV scale new physics contains new sources of CP violation, and precision measurements of flavor observables are generally sensitive to additions to the standard model. So, but let me go to the main subject of my talk, which is rare BD case, which is another deeply connected to flavor. And in a nutshell, what are we looking for? Well, in the standard model, processes that involve flavor changes between 2 up-type quarks, UCT, or between 2 down-type quarks, DSP, are forbidden at the tree level. It can only occur at loop level through penguins and boxes. And so this type of transitions are rare with branching fractions between 10 to the minus 6 and 10 to the minus 10 typically. And what makes it interesting is that a new particle, which is too heavy to be produced at the LHC, can still give sizable effects when exchanged in a loop, as illustrated in these examples. And so the strategy is to use well-predicted observables to look for deviations. And this is an approach which is completely different from that of Atlas and CMS. It is a complementary approach. So to look for the presence of new physics through deviations with respect to precise calculated observables, rare case observables. But let's take a plane and let's fly to Geneva. Let's forget about the pandemic and let's go to the LHC, and which is drawn in this sketch. LHCb is located at point 8 near the airport that you see there. Here is the lake, and let's go down the cavern, and this is what you would have seen until not too long ago. This is an image of the detector as we knew it. The collision point is here, somewhere here. And this is a photoshopped image of the collaboration, which includes about 1,000 authors from over 100 institutes and from 19 countries, and with almost 600 publications, some of them with a very high impact. And the main focus is on heavy quark flavor, but actually there is plenty of other physics in the forward direction besides rare decays, which is the subject of my talk. My take-home message is as following. Precise measurement of flavor observables provide a powerful way to probe for new physics effects beyond the standard model, complementing direct searches for new physics. And this is particularly relevant in the absence of direct collider production of new particles. So it's one of the best things that we can do at the moment. We produced many world record results, and for some topics we have moved from exploration to precision measurement. Most of these results show good compatibility with the standard model, but hints of lepton-flavor universality violation are still persisting. And this has generated a lot of interesting theoretical ideas, and I think you have had an example of that in the talk by Nazila a couple of days ago. But we need more data to test these hints, and the full analysis of Brand 2 is very well advanced, and results on a new analysis that looks at RK and RK star together should appear hopefully soon. And but also results from Atlas and CMS would be very welcome in this domain. And I would like to publicize an Atlas, CMS, and LHCb flavor anomaly workshop that will take place virtually at CERN on the 20th of October with a community of theorists and community of experimentalists in which we look at the flavor anomalies, what one can do at high PT, what one did at LHCb, and what one can do in the future. While we are waiting for the high precision results from the LHCb upgrade and also from Bell 2, of course. Thank you.
I would like to ask you a few questions. Could you say for the general audience what will be the highlight of your talk?
Yeah, well, I work, George, as you know, for an experiment called LHCb, which is measuring antimatter, which for all matter in the universe at the Big Bang, there was predicted to be an equal amount of antimatter, which we don't see in our everyday life. So,
don't see at all, eh?
so what the LHCb experiment is doing is to trying to understand ultimately where the antimatter went. The Big Bang creates equal amount matter and antimatter.
By the
So,
way,
so matter and antimatter behave differently, right?
We should remind that the experiment is at CERN. It's one of the
Yeah, yeah.
4 experiments at
Yeah,
CERN.
it's one of the
LHC experiments.
exactly. It's one of the major 4 experiments at CERN, and I've been working on the experiment now for, gosh, 20 years. I was one of the founding members of the experiment.
I did not know that.
Yeah. And what we try to do, we produce antimatter as well as matter in the LHC collider, and we produce heavy forms of matter. So we're heavy forms of protons and neutrons and electrons, things that are not part of everyday life, but nevertheless they're there in the particle physics world. And we look for small differences. We produce matter and antimatter in equal quantities, and we look for small differences in how they behave. And we find that matter particles decay slightly differently at slightly different rates from their antimatter brothers and sisters, and that makes the difference. And what we're doing is measuring by how much the matter and antimatter behave differently. And so it's something called CP violation, George, which you well know. So I'm going to be reporting for the first time a new observation of CP violation in something called the charm quark system.
I'm looking forward for your talk.
Yeah.
I had quite early interest in CP violation as a theorist.
Yes.
I keep an eye on the subject, but I'm not really working on that anymore.
Yes.
The next question I would like to ask you is, since you have been several times here and you know in depth what we are doing, scientifically and socially and so, just to say to the audience, what is your impression about what we are doing?
Oh, I think it's fantastic, George. I mean, it's bringing together young people, old people like ourselves, together. The interaction with the young people is fantastic. The workshop there's a lot of old friends here. We see each other and we exchange ideas in the sessions and in the in a friendly and nice atmosphere. And we theorists get together with experimentalists. We learn from theorists, they learn from us.
Usually we have top people here.
And the nice thing is as well, the young people get a chance to give talks. And
this takes me to the last question. Should be emphasized that the young people have the opportunity here to give talks.
Yeah.
We try to gather the most talented ones. And what would be your advice to the young researchers?
Oh wow! Absolutely. This is a really exciting time for particle physics. We've just constructed the LHC. We're about to embark on a new phase of LHC, Large Hadron Collider running. We're increasing the luminosity by a big factor. So there's going to be new discoveries. These particle physics experiments run for decades, right? I said I've been working on LHCb for 20 years now, and I won't be working for another 20 years because I'll be retired. But the LHCb experiment will continue, way into the next decade. And then there are new exciting accelerators planned. FCC, and so it's a continuous, sort of mechanism of discoveries, new ideas, and new accelerators going off into the future. And we're getting close. I think closer to the every decade turns up an incredible surprise, right?
So it's a great time for the young people.
For mankind to learn, the fundamental questions of our existence. So, thank you again to the organisers for inviting me back here. It's a wonderful place to be giving a talk, and like everybody else, it's the first time out of the UK for, well, 18 months. So it's great to be back in Corfu. And so I will talk about CP violation and spectroscopy measurements at LHCb. So it's following on from Monica's talk on rare decays. So I'll give a general introduction about what I'm going to be talking about. I will update on new unitarity triangle measurements, in particular the angle gamma. I'll talk about CP violation and mixing in charm. All these are new results. I'll talk about new measurements in spectroscopy, and I can actually skip this, or at least shorten this, because Monica touched on the upgraded detector. So just by way of introduction, I assume everybody is familiar with the unitarity triangle. This was the status in 1995. This was before Barbar and Bell started up. Very little was known. There were measurements from LEP and from NA48. Then Bell and Barbar started up, and of course the picture of the CKM matrix improved considerably, and sin 2 beta was very well measured, and the other parameters of the CKM of the unitarity triangle were also measured better, but not with great precision. So now we come to the present time. This is summer 19, and the LHCb then makes these measurements, and the triangle, of course, is significantly better defined, but yet with certain parameters that are still rather poorly measured, and the angle gamma, this angle here, being one in particular. So that was just an illustration. LHCb have done a recent combination and measured these are the charge B modes where the Ds are going to a whole variety of final states. There are also there are B plus and minus modes, there are B zero modes. For the for charm, there are various modes here that are investigating CP violation in charm. So there are a whole load, and there are also BS modes in the combination. So here we go. So here is the new average. So this is combining all those modes I just showed you. The new error is 65.4 plus 3.8 minus 4.2, to be compared with just to remind you, I showed you before. So, okay, we've improved the statistics a little bit. We are still quite a way away from the indirect constraint. So just to remind you, Barbar and Bell closed with these precisions. So the LHCb measurement of gamma now is completely dominating the world average. So I'm going to quickly go through, changing the topic now. I'm going to talk about exotic spectroscopy. And this is a really nice plot. This is new hadron discoveries at the LHC. All right, and as a function of time. So this is totally new hadron discoveries, baryons, mesons. And, you know, every time you see a dot here, this is a tetraquark, that's a pentaquark, etc. Okay, and it's been an impressive line of discovery over the years. and over 60 new particles. And here they are, but this time it's, so apologies to CMS and Atlas colleagues, this is new hadron discoveries at LHCb, that's new hadron discoveries at the LHC. So we now have 55 of those 60 or so were LHCb. And here are the tetraquarks and the pentaquarks there. Actually, Atlas and CMS got, there are a few up here, including pairs of B quarks that are new from Atlas and CMS. And after a few more years, this is now coming to 2019, it was actually found that one of the pentaquarks actually was two pentaquarks. This was after more data. And here is the 4312. And here we have the established pentaquark states. Now, the thing is, what are these things? Are they really bound states of quarks? Or are they like a molecule, sort of deuterium-like, with a quark, a baryon with a meson, which are forming a molecular state? Or are they some sort of complicated rescattering process, of which I'm not quite sure? But the point is that these new states are actually rather close to the mass thresholds. Here this is sigma c d0 bar. This pentaquark is rather close to the mass threshold there, just below it, right? So it sort of points that it could be a molecular state where you have two, bound state of a sigma plus with a d0 bar. Similarly here, this is close to that threshold. I don't think that one is. The summary, if I may just summarize that we've recorded 9 inverse femtobarns of data. New physics is becoming constrained within the unitarity triangle measurements, but still a way to go on gamma. Fantastic platform for spectroscopy measurements. And these weren't really in LHCb's original physics portfolio. There's still much room for new physics, higher precision required. So we are all working hard towards this new detector where we can increase our statistics at least by between factor of 5 and 10 in the coming years. Thank you.
Could you give us the highlight of your presentation here?
Yes. Well, it is a presentation on something technically called vector-like fermions, which means an extension of the standard model, a very simple one, because you see, one of my main points is that nature is simple, and therefore we should have extensions that are, first of all, testable, that can be tested, because without experiment, our field dies. It's crucial. And I'm very happy that here there is a strong tradition in Corfu of mixing experiment and theory. There are always top people in theory, top people in experiment. And that is, but I don't know if I answer your question. I mean,
well, no, I mean,
yeah,
the vector-like quarks.
Yes, that's one example.
A small example.
Yes, I'll make also a relationship with the right-hand neutrinos.
Yeah,
which
this will be more technical.
Yeah, that's true. In other words, extensions of the standard model that are simple extensions that are plausible, that also can be tested and can solve some of the problems that we still have with the standard model.
The next question is, since you have been so many times here, what is your impression of what we are doing? More or less you commented already, but maybe you could say a little bit more. And also in the prospect that we have discussed so many times of the buildings and so on.
Well, as you know, I have followed since some decades this great effort that you have made to build here in Corfu something that it is sustainable and that looks into the future. And I think that after many, many years of great struggles that you had, now we are coming to the time where things are going to be accomplished. You know, I'm very happy with that. You know, I must say that I told you even personally that sometimes I doubt it. You know, are we going to is George going to be able to achieve this great dream? I can see that things are being done, and that is a great. It gives me great pleasure and pride also.
Hopefully next year we'll be able to offer office space to work and really produce here.
Sure.
And the last question concerns all these young people, young researchers. You brought several.
Yes.
We have our own, and they come all over the world here.
Yes.
I see people even from everywhere, from Mexico.
Yes. I think that Corfu has become a very popular place for many different type of people. For young people, for more senior people, for middle, of career people, everything. And it's getting better and better, I think. And the future is very promising. That's it.
Let me start by thanking the organizers for inviting me. Once more, it's always a pleasure to be here and to see now that there is some results. There are things that George has dreamt about, and now they are being realized. We are hoping that in very near future we are going to have some offices to work and so on. Anyway, I'm going to talk about some aspects of flavor within the context of vector-like works. Okay, this is just, and I will be recalling, the plan of the talk is that I will be recalling some, the dogma of massless neutrinos. You may ask, I'm talking about vector-like works, why am I talking about neutrinos? The reason is because I will argue that vector-like works are sort of cousins of right-handed neutrino, have a lot in common. In right-handed neutrinos, of course, you may say, why you believe in? I believe in seesaw because it's the simplest solution to the neutrino problem. So I believe in simplicity. Okay. Of course, there is no proof that these things are like that. How now? And then I will be talking about how vector-like works violate some of the dogmas of the SCM in a reasonable way. We know that our field was always built out of dogmas that ends abstract past. The most incredible thing is parity. Parity was a good symmetry of electromagnetism. So the best people in our field believed in parity because they understood what it meant, and they believed that it could not be broken. And it's correct to do that because if you understand parity and you see electromagnetism obeying, then you see strong interactions obeying. So it's normal that a guy like one of the best, the very best, like Pauli, he believed that parity cannot, only a silly guy could violate parity. And then the two young guys at the moment, T.D. Lee and CNN, asked a very simple question. Is there any experimental evidence that weak interactions violate parity? And they look at the literature and said that no, there is no. So they propose a very simple thing, which is let us test in weak interaction whether parity is violated. So it's important to believe that simple questions in presence of prejudices can lead to great discoveries. So the standard model is 50 years old, you know. I mean, you may ask, why am I talking about 50 years, 71, you know? Because I believe that it started indeed more or less in 1961 with famous paper by Glashow, who was a student of Schwinger. So we have to give credit to Schwinger to give this smart guy a nice problem. And then it ended, in my opinion, in 1971. So it took 10 years to give birth, you know. Now you may ask, why 71? To answer that question, I would ask a very simple question, which is the following. What were particle physicists doing in 1968? You know, the best way of knowing that, without inventing, is going to the proceedings of ISHEP. You know, I'm very bad at going at searching things in the net, but CERN is a wonderful institution that sometimes gives for free the old proceedings. It's a thick book. So I got it in the corridor of CERN, you know, this for our library, okay? And it's incredible. I was looking, it's certainly one of the most, I'm sorry. I'm sorry, I don't know why. Yeah, some of the most incredible conferences of all times, you know. The number of Nobel Prizes, already Nobel, or that will get that got later on a Nobel Prize is 19. You know, we don't have conferences of that type these days, you know. And nobody in 1968, remember, the paper of Glashow was already there, the paper of Salam and the Weinberg were already there. Nobody was working in gauge theories. In this respect, we have to give credit to Tini Veltman. That's a good student to look at the normalizability of gauge theory. It's not the only one, of course. Other people have tried, didn't succeed, but nobody was working on gauge theories in 1968. It's an incredible thing. So in spite of recent Flavour anomalies that have been described in a beautiful way in previous talks by Monica, and the development ruled out the standard model, you know, the development that ruled out standard model was discovered neutrino oscillations, indicating at least two neutrinos have non-zero mass. What is the key message, in my opinion, of course, everything that I'm saying is in my opinion, I don't have a proof, you know. What is the key message that nature is telling us so far? Choose simplicity. What do I mean? I mean the following. The SM is almost the simplest possibility to put together charged current interactions and electromagnetism, okay? But, you know, if it's, why do I say that the standard model is almost the simplest possibility? Let us recall lepton quark symmetry. And if you wrote in the blackboard ever the fermions of the standard model, you immediately see that the lepton quark symmetry is violated. Nu R does not appear. There is no profound reason for nu R not to be there. So what I will argue is that, I'm sorry, the neutrino nu SM is simpler. What is the nu SM? Is the standard model plus nu R. Then the following, if you follow the rules are, as you remember, is write the most general Lagrangian that is consistent with normalizability and gauge invariance. That has to include, that in itself has to include nu R. Then the following the rules, one has to include the term M nu R T C nu R, which is right-handed Majorana mass to the nu R. And immediately, with nothing else, you have the seesaw already there. Okay? So the standard model is very, if you follow the rules, you don't have prejudice, don't eliminate nu R, then you have the seesaw mechanism already there, okay? So I was a student in City College. Many people don't know what City College is. So let me say in 1 minute what is City College. City College is continuation of Bronx School of Science. I'm sure that everyone knows that Bronx School of Science, where guys like Glashow and Weinberg studied, okay? And the continuation of Bronx School of Science is City College, okay? I will come to the question later on. So Marshak, who became president of City College, and used to meet with students at 8 o'clock in the morning, students and professors, like Mohapatra and Sakita, Kikawa, people that later on did superstring. That we used to meet with Marshak, and he used to ask us the following question: why they means Glasser and Weinberg, put a new R in their pocket? That was the question that he used to ask them. Now, what happens now with vector-like works? So, vector-like works are very similar to new R. If you consider an extension of SM, which I was considering new quarks of charges Q minus 1/3 of Q 2/3 just for simplicity, if they are introduced, immediately you have, similar to what happens with the Latin neutrinos, SU2 corresponding invariant terms like this. They are not protected by the gauge symmetry, therefore they can be naturally large. And the simplest possibility, of course, is to assume that VLQs are isosinglets. I always choose the simplest possibilities. If you do that, then immediately a new scale is introduced. So this scale can be above the electroweak symmetry scale, similar to what happens with nu R. Okay, so again, in the seesaw, 3x3 unitarity of PM&S is violated. This is an important thing. That's why this neutral current appears. So in the vector-like works, the same thing happens. They are violated, but violations are naturally small. Therefore, we should not be afraid of violating the dogmas if you have a mechanism to make it natural. Now, a crucial question, of course, is what can VLQs do for you? Apart from being natural and so on. They provide a simple alternative solution to the Strong-CP problem without actions. There are many possibilities that were considered. The simplest one, in my opinion, is one of Barr and Nelson, Nelson-Barr mechanism for having models with solution of the Strong-CP problem. They provide the simplest extension of the SM with spontaneous CP violation. I will come to this question. It's very simple to construct a model with spontaneous CP violation, but where CKM is non-real. We heard this morning the talk about by Harnew about CKM, and we know that CKM has to be complex. Why? Because of gamma. No, not the other thing. Not what the asymmetries in Fleck and in Bell and Babar. That is not enough, because they are measuring beta, and beta it can be there even if CKM is real. Okay, but gamma it will be very difficult. I will not say impossible, but there is no reasonable model where CKM is real and gamma is complex. It is not zero. Okay, so gamma is a very important angle. So any model of CP violation has to be able to create a complex CKM. That's not easy. Okay, it's possible, but it's not easy. Conclusions, I can go to conclusions. So we need a guiding principle in the search of new physics. A possible principle is simplicity. And we have argued that the new SM is simpler than the SM and is in agreement with the experiment. Neutrinos should be majority parts, in my opinion, and VLQs are cousins of nu R and may also violate some of the dogmas of SM. Since I have to keep talking about violating dogmas of SM, I should say there is no doubt that SM made by the great masters, Glasser, Weinberg, Salam, and we should include also Braut, Angler, and Higgs. This is the greatest achievement of theoretical physics, after quantum mechanics and relativity. There's nothing. I'm sure that superstring people will be shocked. How can be something? This is by far the greatest achievement of theoretical physics, and the experimental physics. Okay, after relativity and quantum mechanics, in my opinion. Even if they made in the quotes a mild mistake with the nu R, that's a minor thing. Standard model is fantastic. Okay, that's all.